In this video, we're going to look at how to transform atomic structures into the Bohr-Rutherford diagram, in this case where we're able to use various numbering systems, like for example indicating the number of neutrons and protons in the nucleus, and also indicating the number of electrons that is orbiting around the nucleus of an element. So in this particular scenario, we have this atomic structure, and we're going to transform this into some kind of numerical notation that will be important in later lessons relating to identifying various patterns in the periodic table with respect to various elements positioning. Now, in here, we're going to ask ourselves, how can we draw or transform this one right here into this particular notation right there? Now, the first is to be able to draw a circle first to represent the nucleus of an atom, which is indicated as this right here. So once we draw our circle, this circle in here, which represents the nucleus, will contain the number of protons, which is equal to the atomic number, and the number of neutrons, which is the subtraction of the atomic number from the atomic mass. What is the atomic mass? On our previous lesson, we know that the atomic mass actually gives us the average weight or the average mass of a particular atom, and you know that the mass of an atom is solely dependent on the nucleus content, which is the sum of the protons and that of the neutron. So in that particular case, to determine the number of neutrons, we subtract the atomic number, which is equals to the number of protons from the total mass, which is the atomic mass. We don't take into account the electrons, because the electrons is really light and it doesn't account for the mass. It's just highly diffused. So next is to draw a circle around the nucleus that represents the shells. The shells is also equal to or the same as the energy levels, and these energy levels can actually be extracted from the period where our element is positioned. In this particular diagram right here, we have the first shell, which is period 1, second shell period 2, third shell period 3, fourth shell period 4, and we notice that in period 1 we have the maximum of electrons allowed to be equals to 2, second shell maximum amount of electrons to be equals to 8, the third shell maximum number equals to 8, and fourth shell maximum number equals to 8. But because we are going to focus on the first 20 elements, we're just going to stop at 2 electrons in the fourth period. Now let's look at how we can be able to distribute the number of electrons in each shell. So in this case, you follow this numbering pattern, which is for hydrogen we just put 1 electron, but then when you get to helium we actually pair that electron, so it becomes 1, 2 right there. So as you move to the periodic table down the group and across the period, we count to 3, 4, 5, 6 on each quadrant, and then we pair the quadrant that contains the electrons, going 7, 8, 9, 10. So in that case, you are able to continue this flow, going from the second shell to the third shell and to the fourth shell. So let's look at an example of this, which is fluorine. In fluorine, if you look at it in the periodic table, it has 9 protons, and if you also look at it in the periodic table, we see that there is a large number which is equals to 19. This number 19 is the atomic mass, which is acronym to be AM. And so to determine the number of neutrons, we just subtract the proton number from the atomic mass, which is 19 minus 9, which gives us 10 neutrons. So we can also get this particular number 19 from any notation, either where you see F 19 9 or we have F 9 19. So these are the two ways you can actually find those numbers in the periodic table. So let's continue from there. Now we're going to draw our Bohr-Rutherford diagram, and to do that, first we draw our inside circle, which is a nucleus that has 9 protons in it and 10 neutrons in it. And then when we move upward, we actually add our first shell and our second shell because it is in period 2. So once we do that, then we actually add our electrons. We start with 1, 2, then next is 3, 4, 5, 6, 7, 8, and 9. So that is about it for the Bohr-Rutherford diagram of fluorine, and if you can try that on your own for argon, and our practice questions will be doing the same thing but starting with hydrogen all the way to calcium. So by that way you can be able to actually see the distribution of electrons and also how the proton number changes going down the group and across the period, to notice some patterns and also dive more into how these will influence reactions in various chemical processes.